Hi, this is Professor Tiffany Martin with Medical Microbiology, and we are working our way through Chapter 5, and this is Enzymes Part 2. To pick up where we left off, we were talking about cofactors. We talked about inorganic and organic cofactors. Organic cofactors are also called coenzymes, and those are our vitamins and minerals. We talked about some of them being carrier enzymes. Those are the ones that are really good at transferring electrons. We're going to use those in cellular respiration. I wanted to show you this picture. I'd drawn some pictures as well, but this is also probably a better one. We know how I draw. The blue one is the enzyme part. This is the protein that was encoded in the DNA and got transcribed and translated into a protein and made, and this is the enzyme there. This particular enzyme is shown needing a coenzyme to complete that active site. You can see how that fits in. It has to complete the active site and is necessary in order to make a functional active site. This particular enzyme also needs an inorganic cofactor. You can see how that metal ion fits in here as well. And all of this together is going to be a fully functional enzyme, an enzyme that can do its job. So a little bit of vocabulary. When you talk about an enzyme that is made but is not fully functional without cofactors, added cofactors, that particular portion of the enzyme that is made is called the apoenzyme. So that's the protein that gets made, the coenzyme or the organic cofactor, and then the inorganic cofactor as well. Remember, if an enzyme needs a cofactor, it will always need that cofactor to function. Some don't need any cofactors. Some only need an inorganic cofactor. Some need an inorganic plus an organic. Just depends on the enzyme, but whatever it needs, it's going to always need that. Once it gets everything in place to make it fully functional, we refer to it as a holoenzyme. So if the enzyme is made fully functional, you'll just call it an enzyme. But if the portion of the enzyme is not functional, the apoenzyme, once you get all of the factors together, the vocabulary term is holoenzyme. And I think of hollow like whole is what I think, the whole thing. Okay, so what else do we need to talk about with enzymes? I do want to go over naming enzymes, see if you know what some of these do. Enzymes name always end in ACE. Which makes it easy. Love that. So anything that ends in ACE is an enzyme. Dehydrogenase, helicase, all of those things are enzymes. Many times lactase, many times enzymes are named after what it does or what it acts on. So lactase is an enzyme that breaks down lactose. Lactose is the substrate, lactase is the enzyme, and then that lactase acts on the substrate lactose. Dehydrogenase is an enzyme. What do you think that one does? That one actually removes hydrogens, and that one there's an enzyme that we make, humans make, produced in our liver called alcohol dehydrogenase. And what do you think that does? That is an enzyme that removes a hydrogen from alcohol and converts it into something else. So when we take in alcohol, which is a chemical, which is a toxin, which is a poison in certain dosages, when we take in, our body's job is to protect us from it. So goes into our bloodstream, circulates through, goes into the liver, comes in contact with alcohol dehydrogenase that converts it into something that is less toxic and that our body can easily get rid of. That's just something to remind you. And so when we are getting rid of alcohol, if you add in more substrate than you have enzyme, then it's going to take a while to get that alcohol out of your system. The enzyme just can't keep up. So when that happens, you've got these toxins, this poison going around your system, you're going to get side effects from that, right? Errors in judgment, slurred speech, poor coordination, poor decision making, all of these things that come with that are side effects of alcohol things. If we get too much alcohol in the system, you get into alcohol poisoning and can even end in death. When that alcohol comes in our system, it's up to the enzyme to get rid of it. Enzymes are made, they're working as hard as they can, but they can only work so much. So alcohol dehydrogenase made in the liver. It's not made in coffee, it's not made in showers. The only thing that will help you with this is time for that enzyme to bind to the alcohol, convert it, and do its job. So, coffee's not going to help. You know, taking a shower is not going to help, those types of things. So that's just a little lesson, free lesson on that on college and enzymes. Okay, so those are some examples of that. We can also categorize enzymes into two types. We can talk about exoenzymes and endoenzymes. Exo outside, endo inside, that makes sense. Endoenzymes remain and function inside the cell. And that's probably most of them, but there are also exoenzymes, enzymes that are made, but then they get secreted out to the environment and they break down large molecules into smaller ones that can be absorbed. So exoenzymes. Now these are very useful for bacteria, these exoenzymes. Remember, bacteria, prokaryotic cells, kind of out on their own. There may be nutrients outside the bacteria cell that are too large to come inside. Some of these exoenzymes are made so they can break down the nutrients outside the cell, get them into smaller pieces that can then come in and be absorbed. So that's helpful. Some bacteria have exoenzymes that can deactivate antibiotics. So penicillin is present in the environment. If a bacteria makes a particular exoenzyme called beta-lactamase, it can inactivate penicillin, and now I have a bacteria that is resistant to penicillin. And bacteria and their antibiotic resistance is a big issue right now. Okay, so we need to talk about how do you regulate enzymes? And that is, give you the answer, doesn't matter. What determines the rate at which your substrate is catalyzed? How fast can the enzyme do its job? And I spoke about that with the alcohol dehydrogenase. If I have the alcohol come in, if you're taking small amounts, the alcohol dehydrogenase can do its job very quickly and get it done. Which do you think controls the rate of reaction? The amount of enzyme available or the amount of substrate available, or both? And I'll give you a second to think about that. Okay, so let me give you a situation that maybe you can wrap your head around it a little better so you can make sense of this. So let's say we're going to Walmart and I need to get groceries. And back when we actually went to Walmart, because now we can't go anywhere, but whatever. You got to go to Walmart, you got to get groceries. And I finish up and I'm trying to leave Walmart. And I go up to the register and I'm trying to check out, and there are 2 lanes open. That's it, right? And there's long lines, 2 lanes open. Now there's 50 registers, but only 2 are open. Who is determining how quickly I'm going to get out of Walmart? The cashier. However quickly that cashier can do his job, get that done, I'm totally at the mercy of the cashier and getting out of Walmart. So the person working is who is going to control the rate of the reaction. So in this case, the enzyme is doing the job. The enzyme is working. So it's the enzyme that controls the rate of reaction for that. The substrate, I'm there with my cart, I'm just standing there waiting my turn. So the enzyme is going to control the rate of reaction. All right, and that's the answer for this question. However, there are some other factors, okay? If I want to get out of Walmart faster, what is something that could happen? They could open more registers, right? There's 50 of them sitting there. Only got 2 open. If you open more registers, if you produce more enzyme, we can get out of Walmart faster. So open more registers, right? Simple to me, right? I'm just trying to get out of Walmart. And that's a way to do it, producing more enzyme. However, why doesn't Walmart do that? They don't do that because they don't want to pay, 50 people to stand there and just wait on a few customers. There's a cost effectiveness about that. So you don't want to pay more workers than you need to do the job. Otherwise, they'd have to raise their prices, right? So there is a benefit for that. So it's very important to balance that. And a cell has the same thing. It doesn't want to put more effort and energy into producing more enzyme just to have it sitting there and waiting. So there's a balance for that. And the cell needs to be able to control for this, right? You may have, 20 registers open at rush hour, and you may only have 1 or 2 open at 2 o'clock in the morning. One will be open at 2 o'clock in the morning. So you want to control that and factor in. So the cell needs to be able to control the amount of enzyme it produces and when it's working as well. So these are things that go into it. Now, sometimes, say I go to Walmart the day before Thanksgiving, bad decision. But if I did, they may have all 50 registers open and I may still be waiting in line. Why? There's more substrate. There's more customers. There are more customers trying to shop. Even with all the registers open and all the enzymes doing their job, there is too many substrates for the enzymes to get through. So in this case, the enzyme can't go any faster, and the substrate is affecting the rate of the reaction for that. And this is called saturation. When there's so much substrate that the enzyme can't do its job, it's called saturation. So that's what happens when you've had a few too many and your body cannot process it quick enough. You get that saturation. And in case of alcohol, you get those side effects from that. Okay, so controlling the rate of enzymes is important. You don't want to spend money or time or energy on things you don't need, but yet at the same time, you need to have enough to get the job done because alcohol poisoning is a serious thing. So it's a balance, and cells need to be able to control that. So we need to talk about how do enzymes control their rate of reactions? How can we control, or how does a cell control, regulate enzymes? All right, so we're going to talk about a couple of different categories. We're going to talk about allosteric regulation, and that has activators and inhibitors. We're going to talk about competitive inhibition and feedback inhibition. So let's do allosteric regulation first. Allosteric. The prefix allo means other. So this is an allosteric site. This is an other site. Other than what? This is a site on an enzyme. Well, other than the active site. We know what an active site is. That's the site that binds where the substrate is. It's going to do the work. Allosteric is someplace else on that protein, on that enzyme. This is an allosteric site. So when we're talking about allosteric, we can have an allosteric inhibitor. So this is a molecule that binds at this allosteric site, so an allosterically, someplace other than the active site. But remember, we got this 3D conformation, and when you shove something in there, it's going to change the shape. And when that allosteric inhibitor binds, it changes the shape of the active site. You can see that represented in this picture there. So an allosteric inhibitor has changed the shape of the active site. Because it's considered an inhibitor, it's going to inhibit the active site. It's going to stop the active site. So in this case, this has shut down this enzyme's ability to work. It has a distorted active site. The substrate doesn't bind to it anymore. So this is considered allosteric inhibitor. This is when you send your cashiers on break. Send them to lunch. You've got a break in the day. You want to shut down the enzyme. You're not telling them to go home, but you just want to stop it from working for the time period to conserve energy. This is allosteric inhibition. Okay. All right. So we can also have allosteric activation. Because we're talking about a site other than the active site, there are some enzymes that we only want to call them in when we need them. They get made, but their active site is non-functional. It's not capable. It doesn't fit to bind the substrate. So it's made with a non-functional active site. But sometimes we need some help. And in this case, you can have an allosteric activator. Allosteric because it's going to bind somewhere else other besides the active site. And in this case, it's classified as an activator because when it binds, the active site changes shape and now it becomes functional. Now it's going to fit in the substrate. So when the allosteric activator is bound, I get a fully functional enzyme. You can get bound. This is when you call all available cashiers to the front. You get a rush and you pull everybody off of whatever they were doing and bring them to there. You're turning on these enzymes so that they can get the job done and get through rush hour. That is an allosteric activator. Okay, so we have allosteric activation and allosteric inhibition, and both of these are allosteric methods of control. All right, so what else? What other ways do we know that bacteria regulate their enzymes. And many of these are true for eukaryotic cells as well. There's also a way of regulation called competitive inhibitors, so competitive inhibition. In this case, I have an enzyme, but I have a molecule that will bind in the active site. So instead of binding in the active site, in an allosterically somewhere else, it actually binds in the active site and it keeps the substrate from binding. So this is a way you can kind of turn the enzyme off and make sure it's not working. If this molecule binds instead, it won't bind to the substrate from that. Okay, so this may be the coupon lady. This is somebody who's taking up space in the active site and keeping this enzyme from working. You know, I've got nothing against coupons, love me a good coupon, but you know, you're in line and you're suddenly, the lady brings out the book and it's all this stuff and you are stuck. The enzyme is busy. You're never going to get out of Walmart. This is competitive inhibition. It's inhibiting, you're blocking it, it's stopping, inhibiting the enzyme from working, and it's competitive because it's competing for the active site. So it's blocking it in this method. So this is called competitive inhibition. Now this is reversible. The competitive inhibitor won't stay blocked. It'll come off and then the substrate can do that. And it's also a numbers game. If I have a lot of substrate, then my competitive inhibitor, just by numbers, isn't going to bind that often. If I had a bag full of marbles and there were 10 red ones and only one blue one, well, chances are you're going to get a red marble. You know, if there's a lot of substrate, then it's going to outcompete this inhibitor. Now, we take advantage of this method with our drugs. We can actually create a drug that's shaped like the substrate where it binds to the active site. We can create a drug that's designed to fit in that active site. And if that drug is put in the environment, it'll stop the enzyme from working and we can shut down that pathway. Remember, it's a numbers game, so sometimes the substrate will win. So you have to make sure that there's enough drug. You have to increase the dosage. You have to make sure that the drug stays in the system, especially when we're talking about humans. You know, as soon as we put something in our body, it's our body's job to get rid of it. So the drug has to stay in a high enough concentration so it's successfully competing and shuts this down, or at least decreases it from that. But we use this a lot with drugs and bacteria. So this is competitive inhibition. All right, so the last one is called feedback inhibition. And this one starts with the diagram. We'll follow the diagram. This is our normal pathway down this side. So let's see what happens. We have a substrate. We have an enzyme. The enzyme binds. The enzyme binds the substrate. You can see that lock and key, that induced fit as we get the enzyme substrate complex. There is an allosteric site that's being pointed out here, but it's empty. It's not affecting it. The enzyme is functional without it. So this is what normally happens. The enzyme binds the substrate and converts it into an intermediate. So I have an intermediate A. There's another enzyme that binds to intermediate A, converts that into something else. I have a third enzyme that does that and eventually get to an end product. Remember our representative pathway? That's what we just ran down. So I have an end product. But what happens if I have a lot of end product? If I have a lot of this, do I want to spend the energy to make more when I have a plenty, when I have a lot of end product? No, nobody wants to do that. Nobody wants to do work when it's already been done for them. So if we've got a stockpile of our end product here, we don't want to keep this pathway open. We want to tell it to stop. So this end product actually serves as a allosteric inhibitor. You can see it fits into that allosteric site. Okay, so that end product you can see fits into that allosteric site and it changes the shape of the active site, and now the substrate can't bind anymore. So again, this is feedback inhibition. It's a way to control it to save energy from this. It typically will target, remember when we target these different enzymes, that makes a difference too. Typically it targets an enzyme right at the beginning. Why? If I were to target an enzyme down here, Well, I've done pretty much all the work and we don't want to do that. So it's best with this. What we see with competitive inhibition is that it usually targets an enzyme right at the very beginning, first or second step in the pathway, and shuts it down. So all of those ways are regulating enzymes. Okay, so that concludes enzymes. That helps you to understand what they're doing, and we're going to learn a lot about them now, so make sure that you get that down, and we will start on the next video with beginnings of cellular respiration. I'll see you then.